I'm going to talk about the n queens problem. It's a classic computer science problem, first sort of popularized by Dijkstra, the famous computer scientist and mathematician. It's a good example of a problem that we typically solve with backtracking. But before we get into that, let me explain sort of the rules or the background of the problem. So let's say we have a chessboard. Now, a regular chessboard is usually 8 by 8. And in the game, but I'm just using a little bit of a cut down example here. Um, in the game of chess, there's one piece called a queen. In one turn, she can move either as far as she wants horizontally, so on the row, or vertically on the column, or diagonally, so on each of these 4 different diagonals. So she can move anywhere she wants under those sort of constraints, row, column, and diagonal. The n queens problem is, let's say we have, I have a 5 by 5 board, so for a 5 by 5 board, can I find a configuration of placement of the queens such that none of the queens can capture each other via those movement rules? So in chess, you move a piece to another piece to capture it. So here on the left, I have a configuration that works. So this queen is not in conflict on rows, columns, or diagonals. This one is also not in conflict on rows, columns, or diagonals. Same here, here, and here. Versus on the right, these first 2 queens are not in conflict with each other. The third one's fine, but by placing a queen up here, on the diagonal, they can capture each other. So this would not be a viable solution. So we're looking for configurations like the left, but not the ones on the right. So this is our final goal is, say, given an n by n board, can you produce a configuration like this so you can place a queen, n queens on an n by n size board such that none of them conflict with each other. So let's take a look at some other methods for solving problems like divide and conquer. And this will illustrate why this problem is actually more challenging perhaps than it first appears. So divide and conquer, you're typically splitting up problems typically by cutting them in half, but you could be cutting them in quarters or so on and so forth. So you're usually splitting problems. But this is not a viable solution, or it's not it's not a reasonable approach to the problem, because if I take an 8 by 8 and cut it into 4 by 4s, well, if I try placing that solution here in this quadrant over here on the left, well, I can't just place this other solution right next to it because there'll be conflicts in every row. So that doesn't work. I can't. So if I took this solution, put it down here in this quadrant, I couldn't take the second one and put it down here in the bottom quadrant because, well, that would also cause conflicts in every column. So maybe on the diagonals, I could take this chunk, put it over here, take this other chunk, put it down in this bottom right quadrant. However, when I go to produce solutions for these other quadrants, I have to be aware of the other solutions when producing it. That's really the issue, is when I'm producing, say, a solution for a quadrant, I have to know about the solutions used in the other quadrants. So this doesn't really help. We can't just naively break the problem down into smaller problems and put those pieces back together. I mean, you can break it down, but there's no way to put it back together. So how about we just try it one at a time, kind of in this greedy style, right? So here I have a solution to a 5 by 5. This works. Now let's see what happens if I add one more row, one more column. So this is just me increasing the problem size by 1. Well, I still have a problem over here because, okay, here's my original solution. When I add an extra row and column, there's really only one place to put the new queen, right? So I can't pick here, 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 here because of the row constraints. I have to pick this bottom right. Well, that's going to conflict on the diagonal here. Oh, what if I put the row on the top? I'd still end up I end up putting it here, effectively that would still be in conflict with this queen. So we can't just naively build up a solution, from smaller problems one row at a time, and we can't split it, in halves or quarters or something like that either. So what about dynamic programming? Maybe I haven't really actually looked into that, but that's typically not the sort of approach you take for this. Dynamic programming is more intended for optimization, like the traveling salesman, where often finding a solution is not too difficult, but finding the best solution is. So that's usually more of the realm of dynamic programming, is those problems. Well, what about randomization? Actually, we can employ randomization. Of course, the downside to randomization, or randomized methods, is you don't you typically don't have so if there's some question about if there's a solution or not, you'll typically not have a definitive answer, right? You just have confidence. So we're going to use backtracking to deterministically find solutions and determine if there's an answer. So for a blank board, there's we're always going to be able to find solutions so long as the board is above 3 or 4 and above. If it's blank. Now, if there's already pieces on the board, that's kind of a variant of n queens, and that's a problem that each board may or may not have a solution for. But that's a little bit tangential. So let's continue on. So this is typically called a constraint satisfaction problem. So the movement rules of the queens, and really the number of queens too, but it's really just the movement rules are the constraints of this problem. So for each queen, we have row, column, and diagonal constraints based upon, how she moves. What we're going to do here is we're going to structure how we sort of fill out the board. We're going to do it left to right. That is, say we're going to put a queen in a column by herself, because it doesn't make any sense to ever put a second one in, right? So I wouldn't put a queen, say, up in this square because, there's already a queen in this column. So we're going to essentially just satisfy the column constraint by just being careful or systematic about how we place. So we're going to pick column 0, column 1, 2, 3, 4. That way we don't really have to worry about the column constraint so much. We'll only have to worry about the row and the diagonals. Now we can think of this as a graph or a state, or a state with a state space. So what I mean by that, you can imagine this whole thing as effectively a tree, where you have a configuration is just a vertex in that graph/tree. Or you could say this configuration is a state, and then when we apply placing the next queen somewhere in the next column, those are actions we can apply to generate new states based upon our current state. So that'd be the sort of successor view or successor function view, where we have a state, we can generate new states with our successor function and then explore those. So here we have a few concepts also where we have sort of viable states. These would be sort of interior nodes in the tree. And we have some unviable states. So this one there's already conflict in, so we won't need to consider the placement of the queen in these other columns, because there's already conflict here, nothing we're going to do is going to rectify that. And our goal is to look for a terminal state. So a terminal state would be one where we've placed all the queens and there's no conflicts between them. So if we make an empty board our initial state, and our successor function adds in states of placing the queen in the first column, so we could generate 4 since I'm using a 4x4 for this example. For this state, we can generate 4 more. What we're going to do, instead of constructing the whole tree, which would be expensive to say the least, what we'll do is we'll do depth first search effectively in the space of this state, really in the space of this state or this problem. So by applying, if we look at whether it's children of this empty board, well, it's placing a queen here in the first column, first row. Now, this is a viable state because there's, with one queen on the board, there's just no way for there to be conflict. So now we'll generate the children or the successors of this state. So state corresponds to nodes in the tree. Successors correspond to edges, or all the children for a state. So that's how we can sort of build out this tree structure. Anyways, so now we'll apply the successor function to this, generating the children. Also look at the children of this state. It means placing a vertex in this column. Not vertex, excuse me, a queen in that column. So this first one is a dead end, right? By placing here, we violate the row constraint. So now we'll have to undo this work and return back. So that is where we get the term backtracking from. We're essentially trying partial solutions out. When we hit a dead end, we'll just undo that last decision and try a different option. So we place the queen here. That doesn't make any sense. That violates the constraints. We'll backtrack here, place another queen there. Also violates the diagonal constraint. We'll backtrack, place a queen here. This looks like a viable configuration, right? So there's no conflict between these two queens based upon rows, columns, or diagonals. So now we'll generate the successors of this state. That is, find this node's children. So we'll go judge them, judging children. That's always suspect. But anyways, let's move on here. So now we're going to place a queen in this third row. Okay, this one is a dead end. Backtrack. Generate a new successor state. Oh, violation. Backtrack. Try this one out. Backtrack. Try this one. Also problem. Backtrack. So this is what makes the problem sort of challenging is, well, this is a viable state, but all its children are dead ends. So we'll have to backtrack even further. And there's no way to really judge that from here. We just have to go try them out. We try it out. We see they're not viable. So then, okay, this is now effectively a dead end, or at least it's the road to a dead end. Now we need to undo this action of placing a queen down here. We'll move back here. We'll come over here and try the last child for this state. I could go into here. It's going to be another whole subsection of the tree. Again, this whole thing will fail. We'll dead end. Everywhere is going to be non-viable. So we'll have to backtrack here and then backtrack further to this empty state. So all we've determined is placing a queen in this top corner is not a good idea. So now let's move her one row down. Now we'll generate the children or the successors of this state, which is, okay, we have a queen here, violates diagonal, backtrack. In this state, violates row, backtrack. Move here, violates diagonal, backtrack. Place a queen here. Oh, this is viable. Now we'll generate its successors. The first one, is also viable. So now we'll generate its successors. This is giving me a dead end here by placing the queen in this spot. Violates row constraints, we'll backtrack. Now we'll place a queen here in this state, or in this square. That also violates row and diagonal constraints. Backtrack. Now we'll place a queen here. Oh, look at that. We're in a terminal state. We can check that we have, this is a 4x4. We have 4 queens placed. None of them are in conflict with each other. Hey, we found the solution. So really backtracking is simply depth first search in the state space of a particular problem. And we want to use depth first search over, say, breadth first search, because we're just in the constraint satisfaction world, like the n queens, we're just looking for a configuration that works, right? We don't need to generate all of them. We just need to find, one sort of solution to this puzzle. Let's take a look at, I've been talking about placing queens in columns. how are we going to actually represent this? Let me move on from the sort of the high-level pattern of the algorithm to how do we actually going to implement it. We can just use a list, right? So if we're only going to ever put a queen in a column, we can just use a list for the columns and just put the index number of the row. So this means in column 0, because it's the 0th element, we have a queen in row 3. Queen in row 1, queen in row... this should be a 4. Typo, this should be a 4. So that's how we'd represent the problem. So really it's just a list of numbers corresponding to the rows we find the queen in. So let's take a look at some pseudocode for this. This is going to be a little bit different than the other sort of pseudocode solutions. I'm going to make sort of implied use of immutable data structures, which makes this problem much easier to implement. And why is that? Well, let's dig into this. So we're going to have a stack of lists of integers. We'll need to initialize this with the empty board. So that's sort of implied. I didn't explicitly say it here. We have the sort of null solution, meaning we haven't found anything. Now, while there's no solution and the stack is not empty, we're going to get the current state. We're going to check if the state is valid or viable, meaning the placement of the queens is good. So we're going to check the row and column and diagonal constraints here. So if it's a viable placement or valid placement, and now we're going to say, oh, if that's true, we're going to check, is it done? Well, if it's valid and done, well, that's the solution. So let's remember that, and this if, while will be done, we'll just exit out with the solution. If it's not done, so if it's a partial solution, we're going to go through each, I think it makes more sense to replace this instead of column with row. But anyways, we're going to go through each, let's say each possible row number, and we'll append that to the end of our current list. So that by adding one more number to the end of our list, that means, well, we've placed a queen in the appropriate row. So yeah, that it would make more sense, sorry, to replace this with row rather than column. Then we're going to take this new board, this new state, and put it into our stack and continue on. So this, by using a stack, this makes it depth first. So what I'm implying here too is that by appending a number to the end of the list, we're not going to modify, we're not going to mutate a current or some other data structure. We're modifying it or adding to it immutably. So a good usage here would be, well, you could use like a linked list, an immutable linked list. That'd be a pretty good choice. That way they can sort of grow. We can actually kind of have this sort of common prefix, as we have shared linked lists or shared, you can easily tie in this sort of or set up a linked list so you can add new things to it, but it just generates a new list without modifying the past ones. Anyways, that's somewhat of a digression, but anyways, if you use an immutable data structure here for the list, when you append another number on the end, when we go to backtrack, well, that's just sort of implied, so we don't have to do anything if this is invalid. Some other implementations or pseudocodes will have to undo the last operation applied to the state. So we'd have to keep track of which operation we're on, whereas this will just use the stack. So this is perhaps the most simplified, but maybe not quite the most optimal way to do it, but it will work. So yeah, it's simply just depth first search, but we're just going to be generating, this is effectively our successor function for generating new states given the state we're in, and we'll just go until we find one or just run out of things to check. So the genre of this problem again is constraint satisfaction rather than optimization. Now, also, if we're talking about sort of the analysis or how long it runs, that's sort of a tricky question. So the dead ends means not all possibilities or possible placements are considered. So if I go back, over here on the left, I don't need to consider what possible values to put in these last two columns because it's already invalid. And nothing I'm going to do to it will fix that. So we'll have to undo work fundamentally to fix it. But these sort of dead ends mean we don't have to actually explore the full space of all possible arrangements, which is a great benefit. But sort of the downside of backtracking is we don't know exactly how long we expect it to run. If you could say worst case, well, the worst case is to go through all permutations of the list. In practice, it's never going to come close to that. So this is an algorithm or sort of a group of algorithms that can be applied. Backtracking is pretty simple. We can apply it to a lot of different problems, but the sort of downside is we don't really know how long it's going to run. It comes down to how you structure the state space. So I chose to do kind of left to right, putting one queen in a column. But there's other ways to structure it. So depending how I structure it, it'll run for different lengths of time. It might have different dead ends, etc. But so it's tough to determine exactly how many combinations we're going to try. Typically, you're going to have to use something sort of empirical to sort of get a judge for how well it works. On the plus side, though, is we can extend this sort of base idea of just depth first search by adding in pruning. So that just says, well, let's extend this notion of judging how viable a state is. So maybe we can sort of come up with some rules of thumb to look at these other sort of viable states. Like this one, we can see it looks viable here, yet any of its successors or its children are not. Maybe there's a way of just judging the state and kind of getting a good sense of, well, this looks viable, but it really isn't, so we can go ahead and safely prune it. So that notion of pruning, we're going to extend much more in the future. We'll call that, those are typically called branch and bound algorithms. We'll use that for optimization, and I'll give you an example of using that for the traveling salesman. But this is backtracking the solved n queens problem, really classic computer science constraint satisfaction problem. Enjoy.